Okay, folks, this is the last example from section 3.11 that I've got, and it's example number 9 on your note page. I encourage you to go ahead and pause the video and try this problem. Try drawing a picture. Try coming up with an equation that relates everything together, and try to come up with a solution, because that's how it's going to show up on an exam. So give it a shot. Pause the video. When you feel ready to resume, go ahead and press play. Okay, so here's sort of an illustration, I think, that partially shows what's happening. Here we've got a trough. Now this trough measures 10 feet long. That's the length. And we're told that the cross section forms an isosceles triangle that's 3 feet across. Okay, and that there's a height of so 3 feet across, and then a height of 1 foot. So let's see if we can put that there. Let's put the 1 foot here. Let's actually move this dimension and just make a little more sense to put it up here. Okay. So there's the dimensions of this trough, and then of course the water is filling, and I've sort of given you a sense of what the water would form the similar isosceles triangle. In fact, the fact that I said similar kind of gives us a hint as to how to tackle this. So let's figure out what the volume of this water would be, and then we'll see if there's any substitutions we can do. So the volume of the water, well, remember that volume for these prism shapes is simply whatever the shape is, in this case a triangle, multiplied by a dimension of height. So to find the volume of this rectangle, trough of water, we're going to take the area of a triangle, which is 1/2 base times height. So let's see here. Here I've already labeled down here. I've labeled this dimension right here as the height of the water triangle. And let's go ahead and label this base for the base of the water triangle. Okay, so that gives me the area. This is the area of the triangle, right? That is the cross section of the water. And then we've got to multiply it by this third dimension here, which we'll go ahead and call L initially. Okay. Well, this is a fairly complicated looking equation in that we've got volume, and then we have volume is dependent upon 3 separate variables. So any of these variables that we can eliminate will make our problem easier. Well, there's one clear substitution right off the bat. What is that? Well, the base is going to change as this trough fills, and the height is certainly going to change as this trough fills, but what's not going to change? Well, the length of the this segment isn't going to change, because the water is simply filling the space of the container, and the container has a fixed length of 10 feet. So we could go ahead and replace this with a 10 here, because that length is not changing. Okay. I would like to keep going on that vein of trying to do some substitutions, and so for this, let's look at a cross section of this trough. Okay, so I've drawn a picture of the cross section of this triangle, and it's not to scale. But remember, we said that the top of the trough had a width of this 3. I think we're in feet here, and then the max depth of the trough is 1 foot here, and so that gives the outside triangle. Water then fills into the trough, forming a similar triangle. So we're going to take advantage of this similar triangle idea to help us represent the variable b in terms of h. Okay? So this is a clever substitution trick, and like I said, these problems get a little bit harder as we go, mainly because of these substitutions. So let's go ahead and form a statement about this similar triangle. We know that the height of the water, the ratio of the height of the water to the height of the trough, will be equivalent to the width. Let me say, width is fine. The width or the base of the water, and by that I mean I'm talking about this distance right here, over the width of the trough. There's actually lots of ways you could express this ratio. It's just it's important to be consistent. Here I've got a statement about the height of the water. So down here I put the height of the trough, so that means a statement about the width of the water needs to go up top here. There are other ways you could set up this fraction, but it is important that you be consistent. Okay, so now that we've got that, let's go ahead and fill in the variables. The height of the water we are calling h over the height of the trough, which is fixed at 1, and that's equal to the width of the water, which we're calling b, over the width of the trough, which we know to be 3. So we get h is equal to b over 3. Now this is currently solved for the variable h, but remember that the original question is asking how fast is the height of the water changing with respect to time. So if there's a variable we want to eliminate in our substitution, it's not h, because we need that to show up to answer our question. So let's eliminate the variable b here. So to do that, let's multiply both sides by 3. And when we multiply both sides by 3, we get that 3h is equal to b. So we are now going to substitute this into our original volume equation, which was v equals 1/2 base times height times 10. So, sorry, I've had to move around a little bit. I've been trying to work with this video. So we had volume is equal to 1/2 base times height times 10, and as we simplify that, we get volume is equal to 5 base times height. I didn't want to implicitly differentiate this yet because it had the variable b in it, and I could actually replace the variable b through this substitution. So here we go. This gives us that the volume is equal to 5 times the base, but we're replacing the base with 3h times h. So this gives us that the volume is equal to 15h squared. So at long last, we now have a formula that relates the known quantity and the unknown quantity together, so when we implicitly derive them, we'll have the rates of each of them show up. So here we go. This is the procedure. We take the derivative with respect to time of both sides. Okay. When I do so, I get that dv dt is equal to 30h times dh dt. Okay. Well, if we go back up, and this is getting a little lengthy, if we go back up to our problem statement, we were told that water is filling into the trough at a rate of 12 feet cubed per minute. That's how fast our volume is changing. So that right there is our dv dt. And we're told that currently the water is 6 inches deep. So if we go down to our related rates equation that we came up with, dv dt we said is 12, and this is equal to 30 times h. And be careful here, this is 12 cubic feet. Everything that we've been doing so far has been in terms of feet, so that it means our height is actually should be considered as half a foot times dh dt. So we get that 12 is equal to 15 dh dt, or that dh dt is equal to 12/15. This reduces down. Let's see here. We could divide 3 into both of those. So we get that dh dt is 4/5. And what are my units on that? That would be 4/5 of a foot per minute, which is how quickly the trough is currently being filled.